Okay. On Thursday, we started with the definition of a logarithm, and this is the beginning of it. Okay. Every logarithm is going to be written as log, and then it'll be a base, a subscript of the b, and then of some number x. Okay. That thing right there is an exponent. Okay. And what we mean by that is that this thing right here in the box is the value, which we're going to redefine as y, that we take the base b and raise it to. So we're going to take b and raise it to y, which is exactly the same thing as what's in the box, right? Because that's what an equation is. Okay, basically an equation is us being able to say, this thing over here, we can actually rewrite it as y. Okay, but that is the value that we take this base and raise it to get this number right here, x. Okay, so we talked the other day, like if I gave you like log base 5 of, let's just say, 35, okay? That is a symbol for another number. That is a symbol for the number that we take 5 and raise it to get 35. So when we talk about what that specific value is, and this is what I suggest, I'm going to go through this real quick again with you using Desmos, because your TI-83s, your $12, $13 calculators will not do this, okay? So if I'm going to ask you this question, you have to be able to use Desmos to do this. You're going to click on the calculator down here, okay? You go over to where it says functions, go to miscellaneous, come down to log that has the base of A on it, okay? So now I could put 5 there, and what number was I using? 35? And I put 35 there. It gives me 2.209. So that, again, that 2.209 is the number that I take 5 and raise it to 2.20906195512. That's the number I raised 5 to where I can get 35. And 34.9999999 is pretty close. Okay? Does that kind of make sense? Okay, remember what exponents mean. Exponents mean repetitive multiplication, right? And usually so far we've seen exponents that were integers, okay, meaning that I take 5 and multiply it by itself twice. Or I take 5 and I multiply it by itself 3 times, so it's 5 times 5, or 5 times 5 times 5. Here, it's still repetitive multiplication, but I'm multiplying 5 by itself 2.20906195512 times. Okay, and there's really no other way that I can write that specifically with multiplication other than to use these exponents. Okay, so that's what a logarithm is. Is that okay with everybody? All right. So we spent some time on Thursday, and you should have spent some time Friday as well in the assignment, going back and forth between a logarithm and an exponent. Okay, so here, with this example, they're starting with this format and ask you to rewrite it as a logarithm. So when I write this double arrow right here, okay, it stands in for the phrase, mathematical phrase that says if and only if, okay, which basically means that whenever you see that wording, if and only if, in a statement in mathematics, that you can reverse that statement. You can use it left to right, so I'd go from a logarithm to the exponential version, or you can work with that statement right to left. So you can start with the exponential phrase and convert it into the logarithmic. Does that make sense? Okay. So I want to take this thing right here, and I want to rewrite it as a logarithm. So what I like to do is I just because I think it's easier to convert and put things in the right position. On my homework, what I would do is I would write this rule first. I'm going to write log base b of x equals y. Then I'll put my if and only if arrow. And then I'll say b to the y equals x. Then I will rewrite it in the reverse order. I'll write b to the y equals x, if and only if log base b of x equals y. And I just choose either the red one or the purple one based on what I start with. I always like to read these things left to right. Okay? But that's what that arrow means in the middle, is that you can read this, you can rewrite it either way that you want, and it still be true. So I'm going to start with the purple one here, because that's what this format is. Does that make sense? Okay? Now, because of the symmetric property of equality, can I rewrite this red or this one here as 5 to the 4th equals 625? Does that say the same thing? And that might be easier for us to decide where does the b, the x, and the y, what are those things when I rewrite this as a logarithm? Because now you can see b is the 5, right? So when I write this as a log, I'm going to write log. So b is 5, so that goes down right there. Okay, the y, okay, which is this 4 right here, right? Okay, that y and that 4, when I write it as a log, is the y over here, right? So I put 4 there. And now what number should go right here? It says x should go there, right? Well, the x in our problem, our specific x is 625, so 625 should go right there. Okay. Now, let's see. So what we're saying then is that when somebody tells me that 625 equals 5 to the 4th, they're telling me then that the log base 5 of 625 is the number 4. So let's take our Desmos calculator, and let's see that. Let's say if I take log base 5 of 625, does it give me 4? Okay. And what that means, remember what that means, it tells me I'm taking 5, raising it to the 4th power. So I'm taking 5 times 5 times 5 times 5 times 5, and it should give me back to 625. And in that case, that's a nice one because I'm multiplying 5 by itself an integer amount of times, okay? Which is then easier to realize. Does that kind of make sense? Okay. Here's another one. Okay, now it's a little bit different, so I'm going to rewrite it again. So it's the purple one. Okay, it's the exponential version. We're changing to a logarithm. So I'm going to rewrite it though. I like my exponent part to come first. So I'll rewrite 1/2 to -2 is equal to 4. So now I'm going to write this as, so my 1/2 is the base, right? So I'll say log, my base is 1/2. Okay. The y is this -2, correct? And now the x value, what goes here? 4. A lot of times when we write a base here of 0.5 or 1/2, we'll probably write it as 0.5. Just be a little bit easier. And then we're seeing log base 1/2 of 4 does end up giving me -2. Okay. I think a lot of times, guys, what people lose out on or what they miss with logarithms is the end game. What are we doing this for? Okay. Eventually, there's going to be equations that have exponents that are variables. Okay. So, for instance, I might have an equation that says, let's say that we have one of those interest equations that we're talking about. Let's say I had $1,000. I had an interest rate of, let's just say, 3%. So I should write this as 1 plus 0.03 as this. And let's say that I want that $1,000, I want it to turn into $1,200. At that interest rate, I can solve for T. I want to solve for T. I want to figure out how many years should that sit in that account. The only way that we can solve for T is to use logarithms. Okay? So that's our end game here. We're not going to be there. We're not going to be able to get to that for a couple more days. But that is the goal. Is why are we doing this stuff? It might seem kind of trivial. I'm just going back from form to form, rewriting numbers in a different format. Okay, and then using Desmos to check if what I wrote in a different format is true. That's 100% exactly what we're doing. But the reason for it is so that when we come back to this, we can say, well, I need to let this thing sit in there for, maybe 5, 10, 15 years. So when I take it out, I have $1,200. Okay. There's no other way to do that. Okay. There's a lot of stuff, like science-wise, that deals with logarithms. Earthquake magnitudes. You guys ever heard of the Richter scale? Okay. Now it's not called the Richter. It's called the Richter scale currently, but it's really not the Richter scale that gets used. Okay. It's Richter scale's old. Term, it's the old test that they use. But Richter scale does what? Measures what? Come on, rock person. It's the intensity of an earthquake. So the Richter scale is earthquake. What's the Fujima? I think it's the Fujima scale. F1, F2, F3, F4, F5. What are those? Scale of a tornado. Okay. Whenever something on is a decibels. You guys know what are decibels? Decibels are intensity of sound, right? Okay. All of those things are measured on logarithmic scales. Okay. Which means like an intensity of a magnitude of, let's say like a 2.3 magnitude earthquake and like a 3.4 magnitude earthquake. Okay. There's only a difference of 1.1, right? But that because it's logarithmic, that is actually saying that the 3.4 earthquake, and we'd have to do the math. We might do the math here eventually. May be thousands of times stronger than the 2.3 earthquake. Does that make sense? And all that stuff is established using logarithms. Logarithms show up in nature a lot. Okay. You guys know what a nautilus shell is? A nautilus shell? I'm going to get you an image here. You ever seen this thing before? Yeah. It's called a nautilus. Okay. So the size of these cavities change on a logarithmic scale. So they're all similar to one another. But what I'm trying to get at, we might not be seeing the use of this until, or the purpose of it, until, a week and a half from now. Okay. As we go through, there's some notation that we have to pay attention to. Some logarithms will not have a base. Okay, or at least the base will not be expressed to you. Okay. So if the base is not written, the logarithm that is being used is called the common log. Okay. Common referring to as like the usual, right? Whenever something is common, it's just usual. That's what we expect. Okay. So when we're talking about the common log, it is an understood base of 10. Okay. So when I write something like this, when it says log of 10,000 right here, okay, is there a base being written right there? Do you see numbers right here as the base? No. Okay. So that tells me that the base is the common log, which is 10. Okay. So if I go log, when we see it expressed that way, that's one thing. But we'll never do the work without it being there. So I'm going to write it as 10. It's kind of like when I see x. What's the exponent for x? It's 1, right? What's the coefficient for x? It's 1, right? But do I ever, when I write like x plus 3, do I ever write it as 1, x to the first plus 3, like to the first? Do I ever do that? No. Okay? They're just understood values. With the logarithm, it's the same thing. The understood value is just a 10 now. But when and I'm not saying you have to do this, but I think it's safe. When I want to figure out what this is, okay, when I change this into exponential format, okay, I am going to say, okay, 10. So I'm going to write that 10, because remember, 10 raised to the what value, so that is my y now, comes back and gives me 10,000. So that's the procedure from going log base b of x equals y into exponential is b to the y equals x. That's using that format of the rule. Does anybody know what I need to multiply 10 by? How many times to multiply 10 by itself to get 10,000? When I multiply by 10, if I take 3, what? If I take, just hear me out on this. If I take 3 and multiply it by 10, what's that number turn into? 30. Multiply 30 by 10, what's that turn into? 300. How many more zeros does 30 have than 3 had? But that's not what I raise it to. That's not. I don't multiply 10 by 100. No, I said how many times do I multiply 10 by itself to get? So okay. So going off what you said, then you said I'm going to multiply 10 by 100 to get 10,000 because you know you need 3 more zeros. So 100 is what power? Okay, so how can I? That still can't make it to that. Well, no. Okay, so you multiply. If I multiply 10 by 100, I don't get 10,000 because I only get 1,000. I multiply 10 by 1,000 to get 10,000, right? Okay, so you're saying so 1,000 is 100 times 10, right? Okay, but 100 was 10 times 10, right? Times the 10 that's already there, times the 10 that was at the beginning. How many 10s is that? 10 to the 4. If I need 4 zeros, then that means I need to multiply 10 by itself 4 times, right? Okay. So when I ask you 10 to the y equals 10,000, what does y have to be? It has to be 4. Okay. Well, so weird route to get to that, but I think the reason for that is because there's confusion on how, when we verbalize something in math, how you guys verbalize it. Does that make sense? There's a difference in the way that it should be verbalized mathematically and in the way that we internalize that on our individual understanding, and that can create confusion. So when I say how many times do I need to multiply 10 by itself to get 10,000, the answer to that is 4. Multiply 10 by itself 4 times. I think you guys internalize that as, what do I need to multiply 10 by to get 10,000? Well, I need to multiply 10 by 1,000 to get 10,000, right? But 1,000 is 10 times 10 times 10. Times that 10 that's already there, that we started with, there's my 4. It's easier to write it as 10 to the 4th. Okay, so now let's take this one. Is this a common log? Is that a common log? What's the base there? What's the base in this problem? On this one, 2. Okay? So when they ask you to evaluate each log using the knowledge about exponents, we're going to say 2. So I don't know what this number is out here. I don't know. I'm trying to evaluate this, trying to get a singular value for this without a calculator. So 2 raised to the what number? Okay, and I can use a question mark, but I could use a variable, right? I could call this y. Say 2 to the y equals, what should 2 to the question mark equal in this case? Come back and equal 16. So what number can I multiply, or how many times can I multiply 2 by itself to get 16? 4 again. Okay. What about 5? 5 raised to the question mark should come back and give me 125, right? 5 raised to the what should give me 125? 5 to the third. Okay. Now let's just, so they get properties eventually that are going to be what might be confused, or might seem like they're confusing, but they should actually be very easy understandings or interpretations of this process. Okay. Now, I'm going to rewrite this a little bit cleaner. You won't see it written this way, but the 2 is my base, but this 2 to the 5, that is that number that should be right there. Does that make sense? I just want to make sure that we understand that whole 2 to the 5, like previously was the 125. Okay? So here's my question. My base raised to the what number will come back and give me 2 to the 5th. What does this number have to be right here so that I get that side right there? It has to be 5. Has to be. Okay? So what am I saying here? This is a property that becomes very useful for us. If I say log base b of b to the, let's just use x. If I ever have something written that way, the log base b of b to the x. If that thing right there and that thing right there are the same, then my answer is always x. We'll see if that makes sense visually here with Desmos. Let's say I go log base b of b to the, let's just say r here. Okay, now I got to create sliders for all of these things. Okay. And let's just actually go, let's make base, let's make a specific value. So if I put 2's there, okay? If I put r in here, r right now is 1. Does this thing here spit back 1? If r is 1.2, does it spit back 1.2? 3.5, spit back 3.5? Does it always spit back the number that I'm choosing for r? And it shouldn't matter So I'm just saying R because I want to be able to show that that thing changes. So really what I'm saying here is instead of R, 6.6. Does it spit back? Because that base and that number there are both 5. Do I get 6.6 back? So if it's 6.7, still gives me 6.7. If it's 123, spits back 123. So I'm just putting R in there. I can use any letter I want to, so that when I change, so this is allowing it to change, it's putting that R right there now. It's putting that R right there now. And you're seeing that as that R changes, the outcome is still always whatever R was. Does that make sense? Now, even works with those negative values. Okay? So no matter what number I choose for R, that logarithm will produce just R for me. Okay? So I'm always going to get back to something like this. I'm always going to get back. This is called a one-to-one correspondence. So I got to make the left-hand side identical to the right-hand side then whatever's in that position right there has to be exactly the same as what's in that position right there. Is that okay with everybody? Here's another property that's useful. Log, let's say base 5, it's not 5, log base 5 of 1 is equal to what can I raise 5 to so that turns into 1 using exponents? 5. So both those, so you're saying fraction because it needed to be smaller than 5, right? But if I go through all my, so any fraction between 0 and 1 is essentially probably what you meant. If I go through all of those, I do get numbers that are smaller than 5, but I don't get to 1. But you're on the right track. If I use 0, by definition, we said 5 to the 0 is 1, right? Okay. What if I go log base 6 to get 1? What do I need to raise 6 to get 1? 0. What about log base 7? 7 raised to the what will give me 1? 7 raised to the 0. Okay. So every time that you see, so this is the rule, log of any base, and you're getting back 1, then the answer to that thing is 0. Say it again. Because if we go, like we know, like let's just look at, try the best way to answer your question here. So there's a couple different ways. So if I say like 7 to the third, that's 7 times 7 times 7, right? 7 squared, 7 times 7, 7 to the first, just 7, right? So now the question is, well, what do we let 7 to the 0 equal, right? Hold on. So what we do is we end up looking at the other side of things, okay? So I'm going to say 7 to the negative 3, 7 to the negative 2, 7 to the negative 1. 7 to the negative 3 is 1 over 7 times 1 over 7 times 1 over 7, right? Okay. So now that is, 49 times 7 is 343. So 1 over 343. I'll put that as a decimal real quick. Is 0.0029. Okay. 7 squared would be, so, and this is because we know this is 1 over 7 squared, right? With the negative exponent. So it's going to be 1 over 7 times 1 over 7, which is 1 over 49, which is a decimal. Of 0.020, that's an equal sign, sorry. 0.0204, okay? Now this is 1 over 7, okay? So 1 divided by 7 ends up being 0.14, okay? So then we argue, okay, well, 7 to the 0 then, okay? What happens algebraically, if we let's look at a graph of these. So this is showing you when we have like integer x value or exponents. Let's look at what happens when we look at, say, if Okay. So what I've shown you, right, when we said looking at x being 3, x being 2, x being 1, the idea was when x is 3, let's look at the point 3, 343. Would have been easier if I chose a number like 2 instead for my base, but so that point right there, right? Okay, that is 3, 343, which is 7 to the third. Okay, as that x value starts moving this direction, okay, eventually it's going to be the point 2, 49. So we'll go back down to find that point, 249. Okay, and then the next one was x being 1, 7. Okay, so the idea is, and I'm just going to put up another point on here that I can move around, is that as I look at this point D here, as I move it down, okay, it's moving down and left. Would you agree with that? Okay, and as I move that down, eventually it goes to this x value of 1 and the y value of 7, right? But as I keep moving it, okay, as this number here gets closer and closer to 0 from the right-hand side, what is this number getting closer and closer to? It's getting closer and closer to 1, okay? Now that was using this logic here. So we're guessing that maybe 7 when x is 0. So as I was moving that, this number here was getting closer to 0, and this number was getting closer to 1, right? So now let's look at the same relationship, but let's look at the values from being negative. So I'm going to say if x is less than 0, let's look at 7 raised to the x. And now we get this purple curve. Okay, so here we're seeing that as we move to the left, the x value is becoming 0 and the y value is getting to 1. Does the same thing happen to this point? As I move that to the right, are the x values getting closer to 0? And the y value is getting close to 1, right? So that idea, that's calculus, okay? But that calculus is telling us that because from the right-hand side and from the left-hand side, as we kind of narrow in or squeeze in on an x value of 0 from the left, and we squeeze in on an x value of 0 from the right, the y value from the left and the y value from the right both approach the same number of 1. So that tells us then 7 to the 0 is indeed 1. Does that make sense? It's a concept called limits in calculus that maybe allows us best to define that. But that's in a simplified version of that process, why 7 to the 0 is 1, or anything raised to the 0 is 1. Okay, we'll stop there.